Hello, thank you for tuning in. My name is Shima Mohebi, an assistant professor in the Department of Systems Engineering and Operations Research at George Mason University. In this presentation, I'll be talking about decentralized cooperative decision-making and how it can contribute to enhancing the resilience of infrastructure systems. This is a joint work with my former master's student, Catherine Barnett, and PhD student, Babak Aslani. The Department of Homeland Security has identified 16 critical infrastructure sectors necessary for the functionality of the city. If a disruptive event such as a natural disaster happens, the failed components of these infrastructures must be repaired promptly after to restore the city normalcy. The restoration activities use resources such as work crews, money, and supplies. The administrators need to decide resource allocation strategies to minimize the total time for the restoration of infrastructures. Traditional resource allocation models assume the centralization approach in which all geographical areas and infrastructures share one decision maker, one set of resources, and one aggregated goal. However, infrastructures are wholly interdependent and are governed by several sectors working together. Here, you can see a simple visualization for interdependent water transportation infrastructure networks. Pipelines are commonly placed underneath roads, meaning that if a pipe breaks, the co-located road and the transportation network must be damaged to repair the pipe. This leads to competing interests between the transportation and the water sectors, along with separate goals for different physical locations. As a result, it's important to understand the collective behavior of decision makers and decentralization for managing infrastructure systems. In the decentralized decision-making paradigm, individual decision makers are responsible for prioritizing disrupted areas of the network to improve the aggregated resilience. There are several studies in the literature advocating cooperative management strategies to enhance the resilience of infrastructures. However, there is a lack of studies focusing on quantitative modeling the coexistence of cooperation and decentralization for interconnected infrastructure networks. So here we propose a decentralized resource allocation framework for restoring interdependent infrastructure networks based on cooperative game theory. In the framework of cooperative game theory, interdependent infrastructure systems can be modeled as a set of coalitions sharing their resources to restore network components and meet the global performance. In this context, a coalition is a group of connected network components. We consider the nodes of various infrastructure networks as players in our cooperative game. Core and shapely values are main solution concepts for cooperative games. And in this work, we focus on shapely values as a measure of marginal contribution of each node in a coalition. Optimization and game theory methods are two key components in our approach, and they have been applied to the restoration problem of interdependent infrastructures in the literature with different assumptions and applications. So we did a literature review on each modeling approach and tried to identify the gap. A rich stream of the literature for resource allocation optimization problems in interdependent infrastructure network relies on the assumptions of centralized decision-making. In such centralized optimization models, most models seek to maximize the resilience of the network. Some studies in the literature have addressed the decentralized network optimization problem for infrastructures. However, the resulting models are mainly applicable to a small or county-level networks due to the assumptions that all actors are individually making decisions. Also, they do not always incorporate the interdependent nature of the infrastructures to their problems. On game theory approaches, most studies focus on strategic or non-cooperative games. In addition, a weighting scheme needs to be applied to highlight the more critical parts of the infrastructure network to the city. So our proposed model is a cooperative game in weighted graphs coupled with network optimization techniques. Moving on to the analytical part, I would like to briefly talk about the concept of coalitions in our game formulation. We first identify key nodes for each infrastructure networks. For water, the key nodes are valves and pump stations, tanks, or junctions for water main. For transportation, it's intersections connecting highways and bridges. If components are co-located, we add interdependency arcs and connect them in the network. Here you can see a sample coalition for interdependent water and transportation networks, where the key node is a water valve. This coalition comprises two directly connected water nodes to the valve and the co-located transportation node. In our approach, coalitions are determined based on geospatial interdependencies between and within infrastructure networks and the importance of key nodes to the network. After forming the coalitions, the individual contribution of each node to interdependent networks can be calculated based on cooperative game solutions such as Shapley value. As a result, for each coalition, resources can be allocated to disrupted node based on the Shapley value vector. The allocation of resources to nodes will be fair due to the fairness property and axioms of Shapley values. The proposed game is defined between the set of all non-key nodes of interdependent networks. Characteristic function is a measure of the connectedness of non-key nodes to key nodes. And each coalition has at least one key node. If non-key nodes are not exclusively interacting with key nodes, their characteristic function is 0 and do not form a coalition. Coalitional games can be written as a linear combination of unanimity games in a unique way, as you can see here. U sub E is equal to 1 if E is a subset of coalition C and 0 otherwise. The coefficients of the characteristic functions are lambda for all subsets E. We use this characteristic function to identify coalitional structure. After identifying the structures and coalitions, we define a restricted weighted graph that contains coalition C. This allows for weighting different non-key nodes in the individual coalition. The weighted graph must then measure proportional contribution that each coalition contributes after the graph has been weighted. Alpha is a measure of flow, and alpha weighted restricted graph is decomposable on unanimity game. So here you can see the modified characteristic function for the restricted weighted graph. Simply put, this is the value that each node contributes, measured by the amount of flow that goes through the node and accounting the number of routes to the key node, resulting in a vector for each coalition. I should mention that this value will not add to 1, similar to other unanimity games, because of the restricted nature of the graph. We summarize all steps in this algorithm for fair allocation of resources within coalitions. The general flow of the problem starts with the formation of coalitions. We calculate the flow for each link, compute the characteristic function, and use the unanimity game formulation to calculate the Shapley value vector and formulate an order of repair for disrupted nodes based on the decreasing Shapley value. And then we send order of repair to the master problem, which is the network-wide optimization. The optimization of the resource allocation in our work is best described as 2 decomposed problems. One subproblem for coalitions and one master problem that accounts for the entire network. If the coalition has resources available to use, such as local funds, available resources will be applied in that order. If the coalition doesn't have enough resources, The order of repair will be sent to the master problem, the network-wide optimization model. Once the resource is assigned to the coalition, the nodes will be restored, still following the predetermined order of repair. If there are not enough resources to repair all nodes, the subproblem will send the level of disrupted flow remaining back to the master problem. This cycle repeats until the coalition is fully restored. So there is an iterative exchange of information to reduce complexity. I quickly go over notations for the network optimization problem. We have several sets of infrastructures, nodes, supply nodes, transshipments, and arcs. Here you can see the decision variables which are typical for network optimization problems. I would like to draw your attention to alpha and beta on the left side. Alpha is the decision variable that determines when the arc is repaired. We added an additional binary index C to represent if either of the two nodes in the arc are in a coalition. Beta is a decision variable that displays that an arc is restored. An additional index O was added, which represents the repair order determined by the Shapley value. The objective function on the right side is to maximize the met demand. Constraints are added to ensure that the flow in and out of supply, transshipment, and demand nodes match and follow the interdependency rules in our infrastructure networks. The procedures for both subproblem and master problems are summarized in this slide. Once the resource is assigned to the coalition, the nodes will be restored. It's still following the predetermined order of repair. If there are not enough resources to repair all nodes, the subproblem will send the level of disrupted flow remaining back to the master problem. If there is not enough resources to repair all disrupted nodes, a penalty term will be added for unrepaired flow. And this cycle repeats until all coalitions and non-coalitional nodes are restored. For our case study, we used city-scale water distribution and road infrastructure network in Tampa, Florida. There are more than 4,000 nodes in both infrastructures. Key nodes for water include pump, reservoir, valve, and tanks. For transportation, we consider intersections connecting the highways and bridges. Co-located nodes are considered interdependent, and this is mainly because pipelines for the water network run underneath the road. Okay. This table shows an example subset of coalitions in the interdependent networks. In the first coalition, as you can see, one node is from transportation and the rest is from water. The variation in the Shapley values is due to the nature of the characteristic function. Since every coalition calculates its function based on the number of nodes in the coalition and the flow depends on the type of the node, the Shapley values can vary between coalitions, yet remain comparable within the coalition. Then the optimization model was run using Python and Groovy. We created different disruption scenarios with different magnitudes and compared the result to the centralized optimization model. This table summarizes the details of failure scenarios, as well as the objective function values and the computational time for both models. We allowed the models to reach to the optimality for a small failure scenarios, that is 5% and 10% disruptions. In these scenarios, we do not report any optimality gap. However, as the computational time for higher disruption scenarios increases exponentially, we restricted the models by imposing a 5% gap. We can see that the computational time for the 50% scenario and centralized model is more than 37 hours. Therefore, in 12% and 15% scenarios, we report the optimality gap. Overall, as you can see here, there is a significant difference between the computational time of centralized and proposed decentralized models. Additionally, it appears that the proposed method improves the met demand faster than the centralized approach. As you can see here, in 5% scenario, both models start at zero demand met for the water network on the left, but the proposed method outpaces the centralized one in rapid demand growth. And the transportation network for this scenario on the right side, the models also both start at the same demand. The met demand of the proposed model for transportation increases faster, but does end up slightly below the centralized model. The overall demand for the proposed model is better. We observe the same trend for the extreme scenarios of 15% disruptions. In summary, the results demonstrated that the decentralized model outperforms the centralized counterpart in terms of computational time and trajectory of the system performance over time. It also ensures a fair distribution of resources to nodes based on their contribution to the network. In future work, more types of interdependency can be incorporated into the model, reflecting the complexity of the infrastructure networks. Other infrastructures can also be included, such as power networks. And with more extensive networks, the coalition formation procedure could be expanded, either by introducing more key nodes or relaxing the definition of the direct connections. The optimization problem can also be expanded to include the cost to see if the proposed model could reduce the cost of restoring the network. This study is recently published in International Transactions and Operational Research. You may find more technical details in this paper. At the end, I would like to acknowledge our funding agency. This work was partially supported by the U.S. National Science Foundation. Thank you for attending my talk virtually. Please contact me if you have any questions or suggestions.